Thank you very much. I'm sorry for the little delay, and I promise it will be a digestive talk. It should be very easy. I don't know if it's possible to put this like large, the whole thing. Thank you very much. And I would like to thank the organizers for giving me the opportunity to be here the whole semester, because basically everybody I would want to work with is here, and new projects are emerging, and old are progressing. So that's very positive. And today, now I don't know how to change the slides. the clicker. Or oh, this thing? Yeah. Perfect. No. Okay. Yeah, it works. Perfect. Thank you. So this problem, or trying to compute the universal minimum flow of the power set of omega 1 modulo finite, was motivated by an old problem in set theory. That's so-called Katowice problem, because it was asked at a seminar in Katowice. And it's asking seemingly a ridiculous question whether the two algebras, power set of omega modulo finite and power set of omega 1 modulo the ideal of finite set, can be isomorphic. So we would want to say no, but so far we are not able to prove that this is always the case. And it is really specifically to these two cardinals. It cannot be other pair than omega 1. Otherwise, by Baltar and Frankiewicz, the algebras are not isomorphic. So, of course, consistently, the answer is no, and that's whenever 2 to omega is not equal to 2 to omega 1. But there have been some consequences of the possible isomorphism that are proved to be consistent. So, for instance, uncountable strong Q sequence by step runs, and then together another consequence. So both of these consequences were forced, this uncountable strong Q sequence and omega 1 scale by Chodomsky. And another reason why we think rather not is that there is a very trivial automorphism on the omega 1 side. So let's think that this is omega 1 times z, and you are looking coordinate-wise at a shift. So this is just a bijection on a set of size omega 1. And if we have an isomorphism, then transferring this very simple automorphism results in a non-trivial automorphism on the omega side. And it's consistent that all automorphisms of power set of omega modulo fin are trivial, meaning induced by an almost permutation on omega, for instance, under PFA. So that was my motivation to actually look at the groups of automorphisms and see what we can do there. I'm not promising any progress on this question so far, but this was the motivation to look at this. So now we are looking at dynamical properties of this group. So what are the objects? We've been hearing about this all the time, so just quickly. We are looking at G-flows, which are just continuous actions of topological groups on compact Hausdorff spaces. And we are investigating minimal flows. So that means those flows that do not have any non-trivial closed invariant subset. And among those, there is a largest one. It means, well, the universal minimal flow, which sees all the other minimal flows from above. That means that if you look at the universal minimal action, and then any other minimal action, then there is a quotient mapping from mg onto m, such that the diagram commutes, so respecting the actions. And it's not difficult to show that the universal minimal flow exists, and in the world of compact Hausdorff spaces, it is unique up to an isomorphism. But very often, we do not have specific explicit representations of these spaces. So that's a big area of research, and a lot of examples were given by this big paper by Kechris, Pestov, Tudorčević, connecting Ramsey property, model theory, and topological dynamics. And this talk is within the scope of this field now emerging. So let's look at automorphisms groups and the space of linear orderings. So The linear orderings, as Claude was saying yesterday, it's not clear exactly what their role is, but here I'm talking only about those and not the precompact expansions for simplicity, but we will look at something that is not a linear order too. So what is the group of automorphisms? Where we look at a structure with discrete topology. The structure doesn't need to be countable. Well, my structures are not. So usually we were looking at countable. These are not. H of A are all finitely generated substructures of A, and we equip the group of automorphisms with pointwise topology. That means that the topology is generated by neighborhoods of the identity that are open subgroups, which are stabilizers of finitely generated substructures. And the spaces that are explicit representations of universal minimum flow of many automorphism groups are subspaces of the space of linear orderings. So what the action is, well, we just take the ordering and shift it by the action. And we are lucky that the power set of omega modulo finite and power set of omega 1 modulo finite are nicely behaving structures, and we will be looking at expansions of their H, it means finitely generated, finite Boolean algebras, expanded by linear orders. And but these expansions will be nice in a way that we can forget them. So we add them and then we forget them. Add them for rigidity, but forgetfulness gives us a simpler approach. So what does it mean? It means that if we arbitrarily put linear orderings, that should be k-less over there, that we allow, so are in the k-less class, and the original structures in B are isomorphic, then they are also isomorphic after adding a linear order. So we don't change isomorphism types. And just a remark, that what we need to be looking at omega homogeneous structures, and that is important, so that's why I stress it out. Omega homogeneous means that every partial, finite partial automorphism can be extended to full automorphism, and as we've heard before, every group of automorphisms is a group of automorphisms of omega homogeneous relation of structure. And for a countable case, there's this phrase correspondence, so I just put what it means: hereditary property, joint embedding property, and amalgamation property. In my case, I don't want my class to be countable, not necessarily, even though it is, well, it won't be the case for some of the structures, but this only works for countable. Otherwise, we do not have a uniquely determined limit. Okay, so these are the structures we are looking at. And then the major ingredient in here is the Ramsey property, which is what we reduce all these problems to. And just again to remind ourselves, the structural Ramsey property means that if we have a small structure, as Claude was saying, and a medium structure, such that the small can be embedded in the bigger one, and a number of colors, then this arrow notation holds. That means that for every coloring, there is a big structure such that for every coloring of a small structure in the big one by k many colors, there is a monochromatic copy of the middle size structure. And again, the same classes that we've already heard: finite linear orders, that's just standard Ramsey theorem, finite linearly ordered graphs or K-free graphs, ordered hypergraphs, finite Boolean algebras, or finite vector spaces over a finite field. So the first three classes have a linear order on them, and then the last two, not necessarily, but they actually can be also equipped with linear orders that will still satisfy the Ramsey property, but because of the order forgetfulness, it's if and only if. So we actually proved the Ramsey theorem for the linear orders, but we can forget them. And we actually will be thinking about linear orders because we need our structures to be rigid. We need to get rid of all automorphisms. And this is the theorem how to recognize which linear orders are the right ones to give us the universal minimum flow. So this is a theorem from Kekeres-Pestov-Tudorčević for a countable, and it's possible to push it to uncountable, even though one cannot go the same way as the authors did. I've stated only for order forgetful structure because that's what I need here. So we have the automorphism group, an order forgetful omega homogeneous structure. It's locally finite, so finitely generated substructures are finite. And now we are looking at a linear Freise expansion. So Freise, we just need so that we can glue the linear orderings together. It has to be a Ramsey class and consist of rigid structures. So otherwise, we would have a minimal flow, but it wouldn't be the largest one. It wouldn't be the universal one. And then the universal minimal flow is the space of linear orderings on the structure A, such that when we restrict a finite substructure, we end up in our class K. So these are the ones that we allow. And as I said, the class of finite Boolean algebras, which is the H of both power set of omega modulo finite and power set of omega 1 modulo finite. This is a Ramsey class, but it does not consist of rigid elements. So we need to think of some linear orders to satisfy these conditions. And that brings us back to the original question. Well, let's first look at this structure and what is its universal minimal flow. So if the answer to Katowice problem is yes, that means the two algebras can be isomorphic, then of course their universal minimal flows are the same. And this universal minimal flow of the group was computed by Glasner and Gutmann in the topological setting. So in thinking about omega star, which is the checkstone compactification of the naturals minus naturals themselves. And it has a topological description, which is maximal chains of closed subsets in the space omega star. And of course, given this theorem here, it has to have an analog on the algebra and as a space of linear orderings. So what are the right orderings? We order somehow in arbitrary way the atoms of the finite Boolean algebra, and then we extend antilexicographically to the whole algebra. And then the description is that the universal minimum flow is the space of linear orderings that look like this on every finite piece. So these are called natural. So this is if yes, that's been done by Glasner and Gutmann. What if no? What if the two algebras are not the same, which happens most of the time or always? You'll see about that. Well, then it means that power set of omega 1 modulo finite is not homogeneous. Why it's not homogeneous, right? Well, for instance, the 4 elements of algebra, which has the largest amount in the empty set, and then a countable set and uncountable set, well, the algebra doesn't know which one is countable, which one is uncountable. And if I could switch them by automorphism, that means that if I look below here, this is the same as power set of omega modulo finite. Below here, it's power set of omega 1 modulo finite. So that means I would have an isomorphism between these two. So if the answer is no, this is not a homogeneous Boolean algebra, which means that we cannot use the theorem right away. We have to homogenize it. Well, it's very easy what we do. We look at the ideal of countable sets and add such a predicate to the structure, and then we are homogeneous, because when we look at some finite partitioning, two finite partitioning of omega 1 that have the same number of atoms that are countable and uncountable, then we can actually find a bijection that brings one to the other and then just lift it up. So easily homogeneous. And of course, then also the automorphism group of the algebra and the extended structures are exactly the same. So we can just look at the extended one. And what if we look at the H of the extended structure? Well, these are all finite Boolean algebras where we specify which atoms are, or which elements are countable, which atoms are not countable. So just finite Boolean algebras with a non-trivial ideal. I always draw the countable one smaller and then the uncountable bigger. And now linear orders. we don't take all natural ones, but those that where the countable things come before the uncountable ones. And then what we need to show that this class is still a Freysa class, so it actually does work, and furthermore that it's a Ramsey class. Let me just tell you what is the only obstacle that we could see here in comparison to just not using the Ramsey theorem for Boolean algebras. Well, we have these two types. So when we are coloring substructures, then we could be seeing how many countable things go to countable, how many to uncountable. So the only thing that we have to care about is that we always map, when we do the partitioning of the big structure into the small ones, under every uncountable thing there is something countable here. So we have to avoid a pattern. The only pattern would be that we have this separation, so we have to get rid of it. That means so that it's not recognizable up here. This would be A in the Ramsey, and this would be C. As a result, it means that the universal minimum flow of the group of automorphisms of parts of omega 1 modulo finite is the space of linear orderings on the extended structure that are I-natural when restricted to any finite substructure. So exactly analogous. And now, of course, the research should go in a way, can we find a contradiction to Katowice problem from there, from these universal minimum flows. And this brought us to those new classes of finite Boolean algebras with ideals, and to look at which of them are Freysa classes, which of them are Ramsey classes, and trying to find a full list of these. So what we did here was that we chose one ideal, and then if we go to the Freysa limit of the H of this structure, then we get a countable atomless Boolean algebra with a generic ideal on that. Well, when we go to the stone space of the countable atomless Boolean algebra, that's just the Cantor set. And looking at the dual filter to the generic ideal, that gives us some closed subset. And that is, of course, the same as the Cantor set itself. And this is one structure that we can apply the machinery or the theorem to. Then another thing that we can study is looking at multiple ideals on the Boolean algebra. So let's say that now at first they are ordered linearly. So as we are indexed by a linear order, and with a greater index we have a greater ideal. And then on the side of the Freysa limit, we get again the countable atomless Boolean algebra with some generic ideals that are in the same inclusion. And if we go to the dual filters, that give us a chain of closed subsets, a decreasing chain of closed subsets of the Cantor set. And again, we will have the same description of the group of homeomorphisms of the universal minimum flow of the group of homeomorphisms. Or we can look at ideals such that when we take the union, it's a prime ideal, which gives us again a chain of closed subset, but now they are intersecting in a point, and so on. We can take a prime ideal, we get a Cantor set and a point. When we take two ideals, then we take arbitrarily in the algebras, then we get two non-intersecting closed sets, two prime ideals. We can go on and on, but probably not that much more, just getting more. And I need to check that all these are really Ramsey classes, but the three last ones are now in progress, but I think the same proof works. And for instance, what does it mean dynamically? That we can actually push this up not only to the Cantor set, but also to all Cantor cubes of arbitrary weight. So if we look at the group of homeomorphisms of a Cantor cube fixing a point, the universal minimum flow will be a space of maximal chains of closed subsets of the Cantor cube containing the point X. It's the same result, yes. Oh, so it's like 2 to arbitrary kappa. So it's, yeah, arbitrary weight. Doesn't have to be countable. Right, so we have these chains. You start with the point, and then you take a chain of closed subsets And that's the representation that corresponds to the linear orders on the side of the Boolean algebra. Another structure that we can apply this to is when we look at not just power set of omega 1 modulo finite, but power set of kappa modulo the ideal of sets of cardinality less than lambda. And we can, for every cardinality in between, we can plug in one ideal for sets of cardinality at most that index. And here, of course, h of that doesn't need to be countable anymore, right? Because we can be putting on uncountable many of these ideals, but nothing changes because locally everything is done by finite substructures. So we always have only finitely many of them in any Ramsey scenario or Fraser scenario. And then the universal minimum flow of groups of automorphisms of these structures are space of linear orderings on the structure that are, again, I'm sorry, there should be, well, natural meaning now that we respect the order of the ideals and then extend on the atoms and then extend antilexicographically. So what are the questions? So what is the complete list? Complete characterizations of Fraser classes of finite Boolean algebras with ideals. Which of them are Ramsey classes? So that also amounts to, usually when we are proving Ramsey, we really count in the ordering or the thing that rigidifies. So here we could actually really have linear ordering when we have ideals that are not under inclusion. We have to make decisions. So we could have something in I1 intersection I2, then something that is just in I1, something just in I2, and something that is in neither. And then we have a problem what to do with these guys that would actually go in between here if we just put a linear order, and then we wouldn't even have a hereditary property. We definitely wouldn't be able, it wouldn't be even a Fraser class. So we just choose to go two ways. We have a linear order on the things that are in one ideal, linear order on the other part, and incomparable here, and just plug these guys in between here. So it's something a little different. It's not anymore just linear orders, and it's within the scope of the precompact expansions, where the linear orders were the first thing where we knew the Ramsey theorems for, but sometimes we add another structure. And of course, Katowice problem, still open, and still a source of many new results and interesting questions. So can the Boolean algebras power set of omega modulo finite and power set of omega 1 modulo finite be isomorphic in some model? Thank you very much. You mean if I have a group of homeomorphisms of the Cantor set? Or
You have this universal dynamical system, and you can look at the group that fixes a point.
Yeah, group that, you mean homeomorphisms of the Cantor fixing a point? Or? Yeah. Oh, okay. So if there is an extremely amenable subgroup, of course, when
you find this way a lot of
yeah, many more extremely amenable groups. Again, when we yes, that's correct. I didn't want to put another term, but yes, it's a source of, again, many extremely amenable subgroups. Whenever we get the Ramsey property, we get the conditions of the theorem. Then, when we take the structure and put the generic linear ordering on that, the group of automorphisms will be extremely amenable. For the uncountable, it's not clear how to put the. We still need omega homogeneity there too. So in the countable case, it's clear, but in the uncountable, it's not clear, these linear orderings.
Point. Here, in this context, the generic linear ordering is useless. Is useless. You cannot use it as in the countable case, because you don't know. That was, why, if you can use it in a countable case, then you can strengthen the result without forgetfulness. Just
Yeah.
for that code.
Yeah.
And that's exactly the reason, because in the uncountable case you cannot
So what does
generate
it mean you don't know what it is? In what sense?
It means that we do not know whether there is a linear ordering on, for instance, power set of omega modulo finite, right? That we don't know that there is a linear ordering such that the group of automorphisms fixing that would be extremely amenable, and G over the group of automorphisms over that one would be the completion would be the universal minimum flow. So we can have extremely amenable but not useful because we don't know whether there is a homogeneous extension by a linear order. So that's a very interesting question, whether knowing these results, because I don't need the order forgetfulness. You can actually forget it, and you really don't need the ordering. Even if you cannot forget it, you don't need it. But you have to use different proofs. So you only need it in the Ramsey and the rigidity. But in general, whether even if the description of the universal minimum flow is linear orderings, can we find a homogeneous one in there?
Thank you.